workshops in the Caribbean, where you can go to places that you could never usually afford. And I think I'm in the same position sort of intellectually. So I'm beyond my intellectual budget class here, but the reaction will be just the same. You sort of lean back and enjoy yourself. What I'm going to talk about is symmetries in symplectic geometry. Now, there is a very long-standing story about symmetries in symplectic geometry, about groups acting on symplectic manifolds. And the first disclaimer is, this is not at all what I'm talking about, okay? So what I'm talking about is a different kind of symmetry which isn't immediately visible. There is an elementary question, which is, since these symmetries aren't immediately visible, in what language will we talk about them? And that's what will take up essentially this talk. And then there's a second question, which is related to mirror symmetry. Where do these symmetries actually come from? And I will try to say as little about this as I can get away with. But let me suppose that, So, what questions, suppose, are we interested in symplectic geometry? Well, one thing that we've always been interested in is Lagrangian submanifolds. So it's a middle dimension. So this is a real symplectic manifold, a real symplectic form. So we're looking at submanifolds which are isotropic and of the maximal possible dimension, which is half-dimensional, and they're Lagrangian. And I will always assume that these things are closed and oriented. Okay? So what do we know about these submanifolds, for instance, about their possible homology classes, right? So, well, there is this gentleman here. So this implies that, if I take the Poincaré dual of the fundamental class, and I copy it with omega, that is 0. Also, since these are totally real submanifolds, if you take the tangent bundle here as a symplectic vector bundle, but you might just as well call it a complex vector bundle, it's actually the complexification of the tangent bundle. And this implies that the self-intersection number is equal to the Euler characteristic up to some sign, which depends on the dimension n. So these are the obvious things. In spite of the elementary nature of the question, of the great deal of work that it's been done on it, there's very little which we actually know about this in general. For instance, if you take M to be a torus with a constant symplectic form, I couldn't possibly tell you which classes in the middle dimensional homology are actually realized by Lagrangian submanifolds, especially if you are picky about what kind of Lagrangian submanifolds you consider. Now, the reason why we think we can make some kind of progress in this question is because there is a level that goes deeper than these kinds of questions here. So under suitable assumptions, which I'm not going to spell out, one can associate to M. These are pretty serious assumptions, as I'm writing down. For instance, they exclude all compact symplectic manifolds. One can associate to M a differential graded category. DG category over C, the Fukaya category, F of M. Okay? So I'm not going to describe what this is, but it appeared already this morning, but objects are suitably decorated, which means there are some restrictions and some choices of additional data else. And there are two relations between the structure of this category and the the elementary topology. So one restriction is, so if you have this category, right, every object has an endomorphism ring. This is a differential graded category, so this is a chain complex, and in fact a DG algebra, and you can ask what is its cohomology, and in my relatively simple situation, that would just be the ordinary cohomology of L, so that you can read off part of the classical topology from how this behaves purely as an object of this category here. Now, this looks as if the category were, very elementary, but if you ask me, what is this thing here? It's really reasonably hard to describe. It's, localizes, well, has to do with how these two submanifolds intersect, in the sense that if they don't intersect at all, it's zero. Now, one thing I can tell you is what is the Euler characteristic of this guy here. That is up to the same sign as before. That is actually the intersection number. Okay? So, applying, terminology very loosely, you can say that, this category is a categorification of the classical notion of intersection number, which only works for Lagrangian submanifolds. So, hopefully, the other thing that I want to get out is this, because I'm interested in what kind of homology classes Lagrangian submanifolds have. So there's a question of how are objects in this category related to the ordinary homology of the symplectic manifolds. It also has a, so if you take the Grothendieck group of this gentleman here, then that maps to the ordinary homology here. In fact, what happens is that, there's a Chern character which goes into the Hochschild homology, and then there's a further map from the Hochschild homology into homology, and this goes to this in the sense that the K-theory class of this object here goes to the ordinary homology class. Okay? So in principle, if we're interested in understanding Lagrangian submanifolds, what we should do is we should take this category and give a description of this category and classify all objects in it. And then by inspection of these objects, we'll be able to tell what the cohomology rings of Lagrangian submanifolds are and what homology classes they have. Okay? So yeah, well, here's an example. So take M, the cotangent bundle of a sphere. Okay, so then every object of f of m is isomorphic to the standard zero section. Maybe this category admits up and down shifts, so maybe I should say up to shift. Okay? And so this implies something for this case here. Namely, if you have a Lagrangian submanifold with the suitable decorations that allow it to become an object of this guy here, then first of all, it's a rational homology sphere because its endomorphism ring is the same as that of the zero section. And moreover, its homology class is the same as that of the zero section, which means that it has degree 1. Accidentally, the first proof, one of the first proofs of these kinds of results, I haven't written this, there are many names associated to this and its generalizations. One of the first proofs actually embedded this category here into a version of the category of representations of the Kronecker quiver, and then just used the classification, which is a bit of a waste because the representation of the Kronecker quiver are a lot more interesting than this one here. Well, here I really do the Fukaya category. It does not really close down the direct sums. So if you enlarge it, then there will be suitable enlarged versions of this statement. Okay, so let me see, may need a little bit more space. Okay, so I also want to do another example, which is a little bit more interesting, which is the example of T star S1, so so an infinite cylinder. So so there it's not quite as easy to describe f of m itself. So it's an easy use is to sort of look at it from a mirror symmetry perspective. The mirror of C star is C star, and the mirror of this gentleman here, which means that there's some kind of derived equivalence between this and the derived category of coherent sheaves with compact support on this guy here. Maybe I shouldn't call it C star because it's confusing, right? This is here as an algebraic variety, okay? So so of course, a coherent sheaf with compact support on C star is just supported at some point, okay? So in particular, so if X is an object of the Fukaya category of M, such that, object should be a circle, right? So, so its endomorphisms should be the homology of a circle. Then X corresponds to, so first of all, it's indecomposable. So over there, whatever it is, it corresponds to something that's located at a single point. And then these are easy to classify. So then X corresponds to the structure sheaf of a point. In C star. Okay? So, so we classified these objects up to isomorphism over here, therefore up to isomorphism over here, but which objects are they actually? They're actually all the same objects, which is the circle that goes once around, and there is a C star flat bundle on it. So a C flat bundle. And its holonomy just gives you this point in C star where this is located. Okay, I said that, when I said objects are sort of suitably decorated, and one decoration is this flat bundle. And so the choice of this flat bundle. Okay, this is not, of course, a worthwhile result in its own, because you can perfectly well classify circles on a cylinder just by yourself. You don't need the Fukaya category to do this. Okay, one thing that you learn very easy when you start. Excuse me.
You don't really need C-star bundle or U1 bundle, because otherwise you can get two disjoint objects which are isomorphic.
No, actually, in this thing here, because I'm imposing certain conditions that I didn't talk about, you can actually allow C-star bundles. But you can't. What you can't do is you cannot move this circle to disjoin it to itself. For me, that wouldn't be an object. Okay, so then it's okay. Okay, so one thing that you learn very quickly, talking to people in quiver representations, is that beyond some very simple structural example, the classification of objects, even of objects, here I have what I said is I looked at objects in here with a given endomorphism ring, and I want to classify those. That made it possible because there are also more complicated objects in here. But in general, that's not a realistic possibility. Okay. So for instance, if you look at the theory of holomorphic vector bundles on projective space, that is a very difficult subject and essentially full of unsolved questions. So, but one thing that you would help is, if the categories you look at have certain additional symmetries, then you can use the symmetries to say something. So. So let me go into sort of abstract framework, right? So if we have suppose we had a DG category and it had some symmetries, how would that be of any use for the kind of questions that we're interested in? Okay, so let A be a DG category over C. one thing that I want is I want it to be proper, which means that if you take the morphism between two objects, you take its cohomology, it's totally finite dimensional. Okay? So then, so we have this thing here I want to use because in the case of Fukaya categories, it turned out to be related to the homology classes. And I also want to use the Euler characteristics of the Homs, which was related to intersection numbers. And it's a Mukai pairing. So this comes with a pairing. Which takes the Euler, applied to objects, it just gives you the Euler characteristic of the Homs. Okay? So I need one more notion, which Fukaya, one more property that Fukaya categories do have, a certain kind of Calabi-Yau property. Now there are many versions, but A is, let's say A is called weakly Calabi-Yau of dimension n. If you have a kind of Serre duality, a functorial quasi-isomorphism. So if I consider the Homs from x1 to x0, it's quasi-isomorphic to the Homs from x0 to x1, dualized, and in degree n minus star. Okay, so in particular, so this implies, if you apply this to this thing here, is that this pairing, actually, let me just call this pairing by brackets. Okay? Excuse me?
Functorial?
Yes, it's functorial. There's this word here that you can't read says functorial. Okay? You know, in fact, I'm skipping some technical details here, right? Because I'm not telling you which direction. In fact, I'm not asking that there be an arrow between this direction, but some kind of quasi-isomorphism of bimodules over the category. So, so this implies this symmetry property here, which is the same as the symmetry property that the ordinary intersection pairing has. Okay? And one thing that's annoying about this kind of thing when you're trying to use it for fruitful purposes is that, you know, for odd n, you know, the self-intersection of any object is 0, which makes it hard to get a grip on the K-theory class of objects. Okay, so I want to look at, you know, having a symmetry, a continuous symmetry. Let's say an action of the simplest continuous group, which is Gm, okay, on A. Now, what do I mean by this? Well, I'm not going to tell you yet. But you know, instead of trying to build the theory first, let's say what we would want to have from such a notion. Okay? So then there should be a category A equivariant of equivariant objects. Right? So secretly, I'm thinking of something like, you know, A being derived category of coherent sheaves on some variety. The variety has a C star action. Of course, not every sheaf is GM invariant, but there is some associated category of equivariant objects. And it comes with a forgetful functor where you forget that the objects were equivariant. Okay? So, so obviously, you know, if you have an object that's equivariant, you can make it equivariant in different ways by tensoring it with a character of the group. Okay, so this should admit an operation so I call Vk the weight k one-dimensional representation. And so when I look at, suppose I look at two objects which actually come from equivariant objects via this forgetful functor, then, of course, not every endomorphism here is equivariant, but this should decompose into weights, and so this should be sorry, I ran out of space here. So if you consider HOMs into all twisted versions, and then maybe to make the isomorphism functorial, you want a tensor with a dual, then this should be an isomorphism. In fact, there's some underlying canonical map, because this thing here is not supposed to change the associated object in A. Okay? So as a consequence of having these guys here, you'll find that the K-theory of this guy here is a module over the character ring. And we have, so the operation of T is tensoring with V1. So therefore, if you consider the induced map here, okay, so T is set to 1 if you go to A. And let me call this map here star. Okay. So now, the main thing when you make the theory is to sort of define this category A equivariant. And it's very easy to define it and having it do nothing particularly useful because it's too small. Okay? So for instance, you could just say, well, my GM action, however defined, it should act on objects of A. Let me take all objects which are strictly fixed. Okay, and that would, of course, be too small. So we also need a lifting or gluing property. Okay. So this, in this case here, where the group, we're in characteristic 0, the group over C, the group here is reductive. This isn't supposed to be, there isn't supposed to be any hard obstructions to this. Basically, it says that, if an object is a sufficient approximation of being equivariant, you can actually make it equivariant. But let me give you, for instance, an example, okay, of what you want, putting it here in quotation marks, because obviously I haven't built the theory yet, but that's what we want to have. So if you have an object and it satisfies, say, H1 of Hom A XX is 0, and so there are no, it's rigid, and there are no non-trivial automorphisms, then X lies, comes from equivariant. Okay? Very sloppy language. It means it's quasi-isomorphic to an object that lies in the image of this forgetful functor. So the idea being that it's rigid, so therefore it's isomorphic to all its pullbacks. When you look at the isomorphism to all its pullbacks, you may have problems when you go once around the circle, but in this case here you don't. Okay, so let's assume that this is the case. Okay, there's one more thing that I would like my GM actions to satisfy, because I'm working with these categories here that are weakly Calabi-Yau, so I need to explain how my GM action is related to this one here, okay? And so, so we say that the GM action is contracting. So, there's an obvious choice, which is that, you ask for the naive equivariant analog of this thing here. That turns out to be not an interesting notion. But what you want is the abstract algebraic analog to having, an algebraic variety, which is Calabi-Yau, which has a cis direction, which contracts the holomorphic volume form. Okay? So if, so the analog here is oops, and I again ran out of space at the crucial thing. Okay, where the duality works up to tensoring with a weight 1 character. If you want, you can use non-zero, some integer, other integer non-zero weight instead. But okay, so now okay, now let me show you.
Sorry, just procession.
Excuse me.
Maybe you should move the tensor V1 inside X1 tensor.
I think because of properness, it.
V1 maybe.
No. Oh, I'm sorry. Yes, excuse me. Thank you. Yeah. There you go. Okay. Signs are. Okay. So so this is it, and this is all extremely simple. It's simple but effective. Okay, so here's a simple example that. So suppose A admits a contracting GM action, and that this one here is injective, this map here, right? Now, you'll say, well, this is a totally unrealistic assumption. How would I ever know any of this K-theory group? And I admit that in general it's not terribly realistic, but that's not terribly important because there are analogs of the same arguments where you use, Hochschild homology instead of K-theory. So, okay, so let X in ob A be an object be such that the simplest kind of object that you can have in these categories here are the ones whose endomorphisms are the cohomology of a sphere, because you need an endomorphism of degree 0 to make it non-zero, and then by duality you need one of degree n. Okay? So these are the simplest objects. So then its K-theory class is non-zero. Okay? So why is the K-theory class non-zero? Okay, so proof. Okay, so I haven't assumed anything about X, but because, I need to assume that this n is bigger than 1, the dimension. So this object here satisfies the condition of this lifting lemma. So you can lift it to A equivariant. Okay? So there, if I look at this guy here, so that there's an equivariant analog of this Mukai pairing here, which is defined like this. So you count these Euler characteristics of the different weight spaces with powers t to the k. And in our case, this is actually 1 plus or minus, 1 plus minus 1 to the n times t, okay? Because you have the identity endomorphism, which is always of weight 0, and then you have the degree n1, which because of this gentleman here needs to have weight 1, okay? So suppose x is equals 0 in the K-theory of A, then its corresponding equivariant counterpart is a multiple of 1 minus t, right? Because it's in the kernel of the thing that sets t equals to 1. I made an assumption of injectivity. So let me write, yes, I wrote the equivariant. So this guy here is a multiple of 1 minus t squared, okay? But clearly it isn't. So it's the end of the story, okay? And so these arguments happen in all sorts of ways. You know, if you have these several such objects here which have no homes between them, the K-theory classes are linearly independent, and so on. So this is a basic example of how you use this thing. Okay, so now the question is, well, how you use the equivariant structure, exactly, to make applications to these things here. And in fact, this argument here is a really, really basic argument of this sort, because when you look carefully at these functions of t, the only thing that we're using is derivatives at t equals to 1. For instance, there's a paper by Polishuk about sheaves on projective space, which makes very clever use of specialization at roots of unity. So this is really, but just to show you what kind of arguments we can have. Now the question is, what use is this going to be for us for symplectic geometers? Okay, so here's an example. So the Fukaya category of T star Sn, n greater than 1, admits, a contracting GM action. Well, why does it admit it? Well, because there's only one object up to endomorphism, right? So that doesn't quite prove it, but so since there's only one object, I can just abusively think about this as a DG algebra. And actually, I said what the underlying cohomology algebra is, but also at the cochain level, it's true that this is quasi-isomorphic to the endomorphisms of the unique non-trivial objects are cochains on Sn, and Sn is formal. So this is an expression of formality, okay? Now, if you have something that's formal, right, for instance, in this case here, I can just take the GM action that has weight 0 in degree 0 and weight 1 in degree n, and I'm good to go, okay? So second example is a little borderline. It's kind of cheeky. So it's the same for T star S1. Okay? So remember, the Fukaya category of T star S1 is derived equivalent to this gentleman here. Okay? And, so what I want to do here for my own evil purposes is see that the derived category of compactly supported coherent sheaves doesn't actually know that this is a C star, right? It consists of sort of atomic pieces, each of which sees only a formal neighborhood of its own infinitesimal disk. Okay? So I can take a GM action which contracts each of these infinitesimal disks to itself. And that's an allowed action here of GM, and certainly it's a contracting action. Not as pretty as that one here. Now, of course, that does not actually solve anything. Yes?
The isomorphism means it's modular with that.
Yes, that's, well, technically speaking, there's only one object here up to shifts, right? So it's actually, the endomorphism ring of the single object is this one here. There's no reason to make formal enlargements here. Okay. So, okay. Right. So that doesn't exactly show that it was worthwhile doing all this, because these were exactly the cases where I could describe the category explicitly anyway, right? So I have to show that this something makes sense here, and so we have the following lemma here. So this is just an example of this thing. So okay, be a smooth affine variety, which is, in particular, it's a symplectic manifold, but just, so that I don't have to explain a lot of symplectic geometry, I just use the case where things are algebraic varieties. So of complex dimension, at least 3, and with trivial canonical bundle. That's useful for me. So if the Fukaya category of a generic hyperplane section so you take this guy and you cut it through with a generic affine hyperplane, and you get a smooth affine variety one dimension lower, which is, again, is a symplectic manifold, so it has its own Fukaya category, admits a contracting GM action, then so does that of M. Okay? So in other words, if you can you have a sort of dimensional induction procedure, you take a generic hyperplane section. If the Fukaya category has this symmetry, then so does the Fukaya category of the total space. Okay? Now, how is this proved? Well, this is an instance of the use of Picard-Lefschetz theory. So the geometry of M is reconstructed from the geometry of its hyperplane section and certain Lagrangian spheres in the hyperplane sections, which are called the vanishing cycles. Now, this assumption here ensures that the vanishing, so the M is of dimension at least 3, so the hyperplane section of dimension at least 2. So these spheres are spheres of dimension 2 or greater. So as objects of the Fukaya category, this kind of lifting process applies to them, and they automatically become equivariant. And from that, you can sort of induce a group action on the Fukaya category of M. Right. So that is a tricky question. No. Okay? So what happens is that, in order to do this, nobody really knows what the Lagrangian submanifolds are in M. There's no way of actually constructing any. The way how this theorem is proved is that you embed the Fukaya category of M into a larger category, which can be explicitly described in terms of the hyperplane section. So it's pretty clear that, there's the way that you construct the action on the larger category is natural, but you don't know what the Fukaya category of M is. So, and on no account can you go back. So you cannot, if M has a symmetry that says nothing, the hyperplane section can be generically much more complicated. So let me give you an example of a consequence that this has. Okay, so corollary, which I want to take a slightly different class of symplectic manifolds, not affine varieties, but one that comes as Milner fibers. So let M be the Milner fiber of an isolated hypersurface singularity given by this kind of polynomial here, x1 squared plus xk squared plus p xk plus 1 xn plus 1 equals 0, where k is at least 2. So then any Lagrangian sphere in M has non-zero and primitive homology class. Okay? So I should point out that if n is even, this is trivial. See, because every sphere has non-trivial self-intersection. But for n is odd, this is not at all trivial. In fact, it's not clear why there should be, why. If you look at it from the point of view of traditional topology, the even and odd dimensional cases look entirely different. Now, if you look at it from the point of view of singularity theory, it seems that I've actually done nothing here. So this adding of quadratic terms is generally supposed to be a harmless operation, but actually no such thing. Okay? So the Milner fibers of these guys here are enormously simpler than the Milner fibers of P. So how is this theorem proved? Well, so the Milner fiber is obtained by, taking this guy here. So this supposed to has an isolated hypersurface singularity set at the origin. You take a small ball around the origin, you perturb this equation to make it a smooth hypersurface. Then the piece inside that ball, that's the Milner fiber. Okay? So you can take the Milner fiber and essentially apply a generic linear fibration with that. And the situation looks like a local version of that situation there. And the fiber is, again, a Milner fiber. It's what's called the polar variety. It's the Milner fiber of what you get if you take the original singular thing and you slice it by linear hyperplane going through the singularity. Okay? Now, of course, if you slice it with a generic singularity, the rank of the Hessian is preserved as long as it can. So after you slice it for a while, you're left with a Milner fiber of x1 squared plus xk squared equals 0, which is actually a cotangent bundle of a sphere. So that one contains a contracting GM action. Then you induce yourself up, and you apply this kind of very simple algebraic lemma with the 1 minus t squared that I did. Okay? So at least, at least it works for a certain class of spaces. Now, now I want to go back for a second and talk about the foundations for the subject of a second. What do I actually mean by a GM action on A, right? So these are not deep problems, but they're problems which arise when you try to do this. So what is actually a GM action on A, or in fact, say, a G action on A? Say, G is a reductive group. So again, I have to say one thing which is a sort of disclaimer. The natural thing when you think of group actions on categories is to sort of take the relations between the group elements and kind of relax them by introducing homotopies. That is not what I'm talking about here, because in this situation here of a reductive group in characteristic 0, there is nothing to see there. Okay? So my questions, the only difficulties that arise here have to do with the fact that this is actually not a discrete group. Of course, we could pretend that it's a discrete group. So there's a notion of discrete G action. Okay, so you have every element of G gives you a functor, they compose strictly, acts on Homs, and so on. Obvious disadvantage is it doesn't use the fact that G is an algebraic group, so it's a non-starter. Okay, but at least it's something that you can talk about if you want to. Then there's the next obvious notion, which I'm not sure it has a name, but let's call it a rational G action. So which means that the action is trivial on objects, and that if you have two objects, so Hom A is a rational representation of G. In a way that's strictly compatible with la la la. And the obvious disadvantage of this is that, well, this is an action that's trivial on objects, right? So in this case here, well, we could then define this case here, you can define the objects, the equivariant category, just say we keep all objects in all possible ways to make them equivariant. And then the Helms from x0, k0, x1, k1 is a suitable weight space in Helm A, right? Things that have weight k1 minus k0. So that'd be easy, but the problem is that, G actions don't usually work like that. Certainly the actions that we want to define on Fukaya categories do not really leave all objects invariant. Okay? So there's a compromise, which is to say, well, look at the case of algebraic geometry. Suppose I had G, and it's acting on a projective variety, and suppose the action is linearizable, so you have some ample line bundle, that is equivariant. So not every sheaf is equivariant, but you have enough things that are equivariant to reconstruct the entire category. And so if you have a rational G action, so that induces, well, things that are a priori, they're only discrete, but there are some kind of G actions on formal enlargement. E.g., a convenient formal enlargement is the DG category, what's called perf, the category of perfect modules, which are the modules that can be constructed in a finite way from the original objects of A. And then you could say, well, so the action on perf A, of course, doesn't leave, not every module is equivariant. You have some kind of notion of an equivariant module. And this behaves nicely. So in principle, this has only a discrete G action, but it's a discrete action which is somehow nice. Okay? So you can say our notion of category with a G action is either categories of this kind here, or maybe full subcategories of full DG subcategories of these things here. And that sort of works reasonably well as a way to muddle your way through applications. There's an obvious disadvantage here if you work with subcategories here. Suddenly, the notion of category with a G action has no intrinsic description. It depends on embedding it into something which is known to be nicely behaved. So I think a slightly better way is to say the following thing. So what does a G action do? So it takes an object and you pull it back. But G is an algebraic group. So if you pull back the object in all possible ways, it forms a family of objects which is in some sort of sense algebraic. Okay? And so let me call this a G DG category. So the idea is you take these families as a starting point, which means you have objects, and so this is a chain complex of, say, projective CG modules. Okay? So think of this as a sheaf on G, as an algebraic variety. And the idea is that the value of this at a point G is not Helms from x0 to x1, but Helms from pullback of x0 to x1. And then the consequence is that when you do the product, think a little bit. So you have Helms from x1 to x2, tensor. So what is definitely not is it's not a category enriched over this ring of functions, because that wouldn't use the fact that it's a group. So this is a module over CG cross G, and composition will have this form here, where this one here, this tensor product, is where you take the map of rings that's dual to group multiplication. So you pull it back to G cross G, and then there's a G cross G linear map, and there are certain axioms. So this is what it looks like. And I want to show you that this works extremely well. So here, an example. So the DG category, let's say dot, which, yes. Oh, they're all X's. They're all X's and my bad handwriting. Okay, but you're good to tell me because I will need Y's in a second. So it's a DG category that with a single object Y and hom dot from Y to Y is just the ring of functions on G, and this map here is just the identity on CG cross G. Okay? So what this is one object that is isomorphic to all of its pullbacks, because there's a hom of, it's a rank 1 at every point, so and it's isomorphic to all of its pullbacks. It's a one isomorphic object, equivariant object. And now, so G, DG functors. Okay, so between such DG categories, and again, they have some kind of structure like this. Now, DG categories are my friends, but DG functors are not my friends because there aren't enough of them. In particular, there's no inversion of quasi-isomorphisms. So what I like to do is I like to enlarge them, which is no longer shocking. So actually, infinity functors, which have higher order nonlinear terms. Now, the reason why I want to do this is the following definition. An equivariant object, so now A is one of these categories here. An equivariant object of A is a G, A infinity functor from dot to A. Okay? So this is modeled on the definition of homotopy fixed point in algebraic topology. So now let's see what this actually looks like. Okay? So when you spell it out, so there's a unique object here. Let's say it goes to some object X. And then what you have is you have a linear term which looks like this. It's a CG linear, so in fact it's just given by an element of degree 0 here. So let me just call it F1. Okay, and then F2. It's a CG squared. There will be quadratic and higher order terms, which are all just part of the definition of this functor here. So this will be okay. So it's of degree -1, and the constants are extended to G squared. And there's a whole higher order sequence where degrees goes down, the higher powers appear, and they have to satisfy certain equations, which are nonlinear equations. But you can make a theory for there's a sort of 1950s style obstruction theory for solving this order by order, okay? And so this leads to obstructions in HK of G, H star, hom A, XX, whoops, H1 minus K. Okay? So this thing here, I have to do a little bit of explanation. So this thing here is the category after you threw away the equivariance property. So it's the fiber of the previous thing at G equals the identity. So this is just a vector space. And after you have F1 and F2, this vector space will become a rational representation of G. And then the higher order obstructions will appear in this thing here. And of course, if this is a reductive group, these obstructions are all 0. Okay? So, what
do we mean by HK?
Well, it's the cohomology. You have a reductive group, and you have a rational representation. You have the homology of G with coefficients in that representation, as introduced by Hochschild, I think, somewhere in the early 70s. Okay, so it's defined by, taking rational. It's defined using the abelian category of modules over the core algebra CG, which is modules of rational representation. So it's X in this category. And it's given by, usually the classical definition is in terms of some kind of dual bar resolution, which is exactly the thing that you see here. Okay? So this theory here would work in principle well, even if G was not reductive. And it has a great advantage that, these usually, before you see this obstruction theory, you actually have to sweat. But here it's brought to the surface, and similarly, you can make the category of equivariant objects in A as being the category of these functors and natural transformations between them. And it's a very transparent way to think about these things. Okay.
So are you describing the functors from this category simple with one object to
Yes.
A? And this abstraction is kind of the data you have.
No, what I meant is, having defined equivariant objects to be this thing here, if you decode it, the functor consists of these things here. So let me look. I want to show that this definition has the required lifting property. So that if you have an object X with suitable endomorphism group properties, it can actually be lifted. And what I said is that if you set it up in a traditional way using perfect modules or something, there will be some work to do before you land at exactly this point here. And here, the third line will be that you write down this bar complex. Okay, so this is almost the end of the talk. Let me say just one word about the more interesting subject maybe of where these GM actions come from. So far what I've said is, you have one on T star Sn, and then it propagates in various ways. Okay, so the best thing is to think about these things infinitesimally, it turns out. So an infinitesimal GM action is, of course, just a vector field. So in a categorical context, is given by some element in first Hochschild cohomology. And so if I looked at the Hochschild cohomology, let me say, of this Fukaya category of T star Sn, f of T star Sn, in the simple case, n is greater than 1. This has an easy description in terms of the homology of the free loop space of Sn. Okay? So in this degree, here's hh upper 1 goes to hn minus 1. And I can tell you, suppose, for instance, let's look at a two-sphere. So you need a one-parameter family of free loops. What you do is you take a great circle, and you take all possible ways to shorten it, and that gives you a one-parameter family. And that's the same n minus 1 parameter family. Now, the reason why this thing here arises from a point of view of geometry is because this thing here is related to the geodesic flow, and the geodesic flow appears as the flow associated to the structure at infinity of this thing here. Okay? So in all reasonable cases, in particular this case with Milner fibers that I gave you, you can give a sort of geometric explanation in terms of the structure at infinity of the symplectic manifold for where these actions come from infinitesimally. What you cannot show in that way is that the actions integrate to circle actions. So we don't have a geometric description of an integration condition. And also, the geometric theory is just a teeny bit weaker, which means if you look at the case of T star S1, obviously this C star action that I wrote down was geometrically completely unreasonable. And correspondingly, you can't actually find a purely geometric construction for it, the thing that contracts every point separately to itself. But that may not actually be a disadvantage because you can sort of say this was a disgusting thing, which I shouldn't have done anyway. All right, thank you very much. That's right.
And then you have cuts which you have the B curvature, which is clearly necessary.
Yes.
Is there analogous kind of B curvature statements which you can...
So the conjecture says a vector field integrates if the Picard group vanishes on a closed algebraic variety. No, not a closed.
What they say, if you have a vector,
If I have a vector field?
you can consider reduction mode.
Yes.
Now you can consider Picard.
Okay.
And now, if it really integrates,
Yes.
then Picard vanishes. And this is definitely a necessary condition,
Yes.
conjuncturally
Yes.
sufficient condition.
Yes.
So my question is whether you can produce some necessary conditions
Yeah.
for integration. Say, something
Well-
by just consider reduction with P.
So you can certainly consider reduction mod P. And you have the Hochschild homology mod P, which is a subject of study. And after much work, you can now, I don't know actually. I mean, there is work which reproduces, non-trivial mod P structure in this non-commutative geometry situation. I should have a look. Yeah. More questions?